Welcome everyone to the second workshop of the hackathon. Today we're going to talk about how to integrate with signing with Ethereum and signing with Solana with Kristofer Lund, and I am quickly going to add him on stage. Before that, I wanted to quickly reshare the Hackathon link with all of you with a quick reminder that we have several deadlines within the hackathon, the most important of which is a submission deadline in 4 weeks, but we will have an idea submission deadline coming in just 2 weeks. While mandatory, you are just expected to submit us the ideas that you plan on working on, which is going to give us a huge heads up on what you plan to do, what issues you might be having, and we will be then directing you to the people that will be able to give you the most adequate forms of support so that you can convert your ideas into actual submissions. Welcome on stage, Kristofer.
Thank you.
Yeah, feel free to take it away, share your screen. Everyone, if you have any questions throughout the session, please make sure to post them in the questions channel on the bottom right side, or in the chat section, whichever is more convenient to you. Ideally, if there are questions within the questions channel, and Kristofer will be able to come back to them once he enters the Q&A section of today's talk. But yeah, over to you, Kristofer.
Thanks. Yeah, and I'll try throughout the talk also to view the chat as I go along. So if you have a really important question, please interrupt me at any time. So my name is Kristofer. I am a developer that is really interested in cross-chain applications and these chain fusion applications. I'm sort of the opposite of a blockchain maxi in any sense. So I really like the idea of choosing the right tool for the job, and I believe that ICP is really well suited of playing a crucial role in this cross-chain world of ours, with its abilities to sign transactions from many chains, etc. So this workshop is going to be about how to integrate with the sign-in with Ethereum and sign-in with Solana standards. So we're going to look at what those standards are, a little short refresher on IC chain fusion, on why all of this is interesting. And then I'll make a brief demo, or show you a demo application that I built a while back. And then at the end, I'll take some questions as well. In addition to the demo application, I've also built some support libraries to facilitate these flows that I'm talking about. So we can talk about that as well. So what is sign in with Ethereum and sign in with Solana? There should be an S at the second word there, sign in with Solana. So basically it is a standard for how to package messages to be signed with Ethereum and Solana wallets. So it's a standard message format that allows you to log into back-end services using a regular MetaMask or Solana Phantom wallet signature, and it makes it possible for you to let go of not having this centralized identity provider, and also it improves user experience and sort of it improves user experience when you sign the message. As you can see on the screen, the sign in with Ethereum message is quite detailed about what it is. In many cases, when you interact with applications on Ethereum, the explanations can be quite cryptic when you sign messages. But here it quite clearly states what it's about, that you're logging into an application and on which you are a domain, etc. So it's a self-custodied alternative to centralized login providers. And the Web 2 sign-in with Ethereum Flow looks a bit like this, and most likely you have come across this when interacting with some Ethereum application. And the flow starts with the regular Web 2 backend generating this message in the sign-in with Ethereum message format. The second step is that the user in the front-end application signs this message with their blockchain wallet, MetaMask for Ethereum, perhaps, or Phantom for Solana, or some other wallet that supports this standard. Or basically, they can sign it with any wallet that supports Ethereum or Solana. The third step is this signed message is sent back to the backend, where the message is validated, and the signature is validated against the message, and the Ethereum address is recovered again. And once you have found a match that the signature matches the expected signature based on that message, the backend can safely generate some kind of authentication token, a JWT token or something the like, and send that back to the front end. And from there on, the front end can make authenticated backend calls, knowing that they have used their Ethereum or Solana wallet to authenticate themselves. So just a short refresher on chain fusion. What is chain fusion? So the chain fusion is a concept. It's not being introduced by DFINITY or ICP by any means, but it's heavily pushed by DFINITY and ICP. And I believe, like I said, that the internet computer is very well suited to do these kind of chain fusion use cases, and that comes down to primarily three things. Or the three main features of this chain fusion feature set is that the internet computer can integrate with the many other networks, and it can do so thanks to its ability to sign the messages or sign transactions using threshold signatures, using various signature schemes such as ECDSA and soon coming then ED 25519 and BIP 3420, and that is used for Bitcoin ordinals, and ED 25519 will open up the door for Solana, like really deep Solana integration. So basically, a smart contract on the internet computer blockchain can natively hold tokens, make transactions, sign messages on other blockchains, on a large number of blockchains. So therefore, the chain fusion, it's well positioned to be the sort of the center point of bringing these blockchains together. Because in a world where we choose, where where we focus on use case first and then choose technology, and not the opposite way around, that like it often is, that then many applications will be cross-chain applications going forward, because different blockchains have different strengths. Let's just briefly look at how identities look on ICP, because this is something we're going to touch on going forward here. So identities on ICP are called principals. And a principal can represent, identify and represent both a user and a canister. And canisters are what we call the smart contracts on ICP. Usually these user identities are generated using the default identity service provider that DFINITY or the internet computer provides, which is called the Internet Identity Service. This service has cool stuff like WebAuth and passkey support. It supports Ledger, etc. So it's a good identity service. But when we are building applications geared towards the Ethereum community or the Solana community, the people from those communities are really used to using their wallets to sign into applications. So wouldn't it be good if we, instead of using this internet identity service, could use regular message signatures like people are used to? And we can, thanks to the fact that identities can be delegated on the internet computer, and a canister can delegate to a user principal, this identity. I'll go more into detail to how that works. So why is all this interesting? I believe I briefly touched on this before, but I should just summarize that signing with Ethereum plus the Internet Computer. Why is this interesting? It's interesting because this allows to build these what I call full circle cross-chain applications or chain fusion applications. So let's start here at the right-hand side of the screen. We have an Ethereum address as represented or as controlled by your MetaMask wallet. This Ethereum address can control what happens inside an IC canister. This IC canister can in turn be represented by an Ethereum address or a Solana address or a Stellar address. And then it can perform actions back on that the initial chain. So there it can transfer tokens, sign transactions, etc. So that is what I mean by going full circle from Ethereum onto the Internet Computer and then back again. So this allows for a multitude of really cool use cases, such as multi-sig wallets. That if you have used Gnosis Safe, that is basically how it works. You sign a message using your Ethereum wallet, and then that in turn controls another address that does the work for you, provided that you have reached the signature threshold. And functionality like that could very easily be built on the same technology and such, and also like the decentralized exchanges, AI-powered smart contracts. The Internet Computer will be coming out with AI support, etc. And of course, like I mentioned, it's great for onboarding Ethereum and Solana users because they are used to this method of logging in. Need to check up on time. Okay, 15 minutes. So going back to this, the sign in with Ethereum flow, but now looking a little bit more in detail on how that flow would work when we use Internet Computer canisters instead of a regular Web 2 backend. And it doesn't differ that much because that is one of the strengths with the Internet Computer, that the canisters, the smart contracts, can do a lot of what a regular Web 2 backend can do. So first we generate a message in the backend canister, same as with Web 2 backend. The user signs the message. It's sent back to the backend canister to be validated against the signature against the message. And so from here on, the steps differ a little bit. So based on the public key that the user submitted when sending this message back to the canister, the canister creates an identity delegation object that is sent back to the front end. And with access to this identity delegation object, the front end can generate a new identity that is sort of connected to this delegate identity. And from there on, it can make authenticated calls. So here we had a question. ICP-SIWE Flow, in this case, message here represents not there are no transactions involved in this flow. So it's only signatures of messages. So no financial transactions, no cost to the user of doing this. And from now on, it's also worth mentioning that when we're looking at the code base and the demos, etc., I will only be demoing the Ethereum version of this. So to keep things simple, but it works mostly the same for the Solana version. And when looking at the sign-in with Ethereum demo, this is the architecture, roughly. We have in the backend running on the ICP blockchain, we have an application canister, a simple demo canister that just manages user profiles in this case. And then we have the sign-in with Ethereum provider canister. And this provider canister is responsible for validating these sign-in messages and generating the delegate identities, etc. And the reason why this is built as a separate canister is to make the developer experience as good as possible for the developer. Sign-in with Ethereum definitely could be integrated directly into the app canister. But the easy way to get started with this is just to add this pre-built provider canister to your IC project, and then you don't have to do anything at all, basically, in terms of adding code. So it's a pre-built module. And for the front end, the demo front end is a Vite and React application that uses a hook that use SIWE Identity hook support library to make it easy in the front end to interact with the provider canister and generate this identity. And this hook is available on NPM, so the integration in the front end is also really straightforward. In the presentation, I included links to all relevant packages. So both for sign-in with Ethereum and sign-in with Solana, it's basically the top items there are the sign-in with Ethereum, the core support library that you could integrate into your custom-built application canister if you want to. But I do recommend, like I said, to use the pre-built provider canister. And then we have the two support hooks, the use SIWE Identity and SIWS Identity. And then we have two repositories and with the demos. Basically, the demos are exact copies of each other, except for the actual login functionality. And the QR code on the screen, you see there is the QR code to this presentation that is open to anyone. And I do recommend if for the next section of this presentation that scan this code, click on the link, open up the demo repository and follow along in the code. It's much easier than if I just move over to the demo part of things. I'm getting ahead of myself here because we haven't started the thing yet. Let's perhaps briefly have a look.
Just for those of you watching, if all the, as always, all the slides and links will be shared afterwards in the Hacker Pack. So even those that are watching the recording right now, you can head over to the Hacker Pack and extract all the relevant links for the presentation.
It's good to see that we have at least two viewers. I hope you stick around to the end, and I know that this will be recorded as well. So that's good. Let's have a look at how the demo is structured before we start it up. Maybe I can show you here. Okay. The SIWE React demo Rust. Like I said, it's a Vite and React application. It comes with a make file that does the dirty work of spinning up everything. Let me just briefly describe what happens here. So starting an IC application involves two steps. Basically, first you need to start the DFX, you need to start the local replica of the IC blockchain, and then you spin up your application. So in my case, I made a make file to make things easier. And this make file, what it does, it creates the canister. Let's start from the top. It creates the canisters. It deploys this pre-built sign-in with Ethereum provider. It deploys the backend. And the backend doesn't come with any fancy settings or anything, and it deploys the front end, and the same there. It installs the dependencies and then deploys the front end. So when deploying this pre-built canister, we supply it with some settings, and these settings determine how the sign-in with Ethereum login flow will work. So here's the thing that every project will deploy their own provider canister, which is good, because that means, for instance, that the identities generated by this canister will only be valid within the context of your application. So there is no risk of phishing scams, etc. As long as you specify that, and that we do in the target section here, that we say that this the identities generated by this canister will be valid for the provider canister itself and for our demo backend. And we also provide some basic information that will be shown in the sign-in with Ethereum message. Domain context restriction, is that because of web authentication origin? And also this doesn't have anything with WebAuthn to do, the sign-in with Ethereum flow. It just looks at when you sign in with Ethereum message in your browser using MetaMask. MetaMask will look at the details in that message, and it will show you a big red warning if the URL specified in the sign-in with Ethereum message doesn't match the URL for the website that you are on. So it's basically a user protection there. You tie the messages to your specific domain. And then you can give some settings about how long these sessions will last when you start one. So let's start things up. Let's see where. Okay. So first we need to start up the DFX replica. DFX start, clean. We start up a completely new replica of the DFX of the Internet to Computer blockchain. Done, started. And then we make deploy all. And this will take a few seconds when the project builds and installs all the dependencies, etc. So we can follow along, see what happens. We create the backend canister. There's the backend canister. We created the front end canister. So first we just create sort of the placeholders for the canisters. Where these are represented, these are the principles that I mentioned before, these identifiers. So these two canisters have their identifiers, and then finally we have the provider canister, which comes with a bunch of settings. So all canisters created, installing canisters, and then the second step is that we install the built WebAssembly files into the canisters. Blah, 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 blah. Building the Vite React frontend, uploading all the assets to the canister, and almost done. Done. And let's see. So if all is well, I should be able to reload this page. And now this shows the demo frontend hosted locally. So what you see on the screen here is a simple demo. We connect, allows you to connect the wallet and then sign in. So let's start with connecting this wallet. Connect wallet, choosing MetaMask. I guess one of the goals here is to the user should not even know that they are on an internet computer application. That is one of the goals into my mind. Sign in. Once we have connected, we can sign in. And the first step has already happened in the background, where the front end fetches a sign-in message from the backend. And now it's going to display it when I click this button, and we're going to sign it. So here it's displayed with all the details, the same details as I specified in the set of instructions there, that with a message and tying it to a URL, etc. So if this URL would have been different than the URL shown here, that there would have been a big red warning here. So no scam website could fool me into signing this message on the wrong, on a domain name that it's similar to the right one. Sign in. The message is signing, done. So what we have now done is that we have linked my Ethereum wallet with a newly generated Internet Computer Identity Principle. So now we have established a one-to-one link between these two items forever. As long as this canister lives, I can control this, that canister using my Internet identity. So let's, the demo app, like I said, really simple. I can choose a name. Let's call me Oscar, and an image. I can skip that and save, profile, save. That's it. End of demo. That's all there is to it. This is the computer internet identity. And this is the Ethereum address. And now they are linked. So let's start looking under the hood, how all this connects. We had a look at the make file already. So next step, let's look at how the application is structured. We have the back end. Just let me, let's start in the front end. The front end, as I mentioned, a Vite and React front end. I've tried to keep it as simple and as straightforward as possible. Let's start here, main. We are using WAGMI to facilitate the wallet interactions. And then there is the sign in with Ethereum identity provider, and this provider comes from this support package that I mentioned that makes the integration into the front end really straightforward. So we wrap the whole application in this provider, making this identity available throughout the application without us having to do any prop drilling or anything. And we configure it with some information with the service. And this is interesting. The service, this is a declaration, a definition, an interface declaration that is automatically generated when we built the project. So let's have a look here, how that looks. So this interface, the declaration, like I said, it's not created by me. It's automatically generated. But what this makes possible is it's really nice that all interactions with the Internet Computer canisters from the front end are fully typed, which is really nice. So these interfaces and the way how you interact with the canisters is a bit like gRPC. Almost, you make RPC calls that are fully typed from front end to back end and vice versa. So you configure the provider with the service specification and which canister ID you need to know that the canister ID of your provider canister. But that is also automatically generated for you, so you don't have to do anything else than supply the information here. So next up, we have the identity provider. What else? We have an authentication guard. And the only thing that this thing does is basically it uses some stuff from the identity provider, and the identity provider in the context provides some information. Are you logging in? Do you have you already logged in? And some functions to, of course, to trigger the login flow, etc. So basically, what this component does is that if you haven't logged in, show the login page, and the login page. It's basically everything here is mostly JSX and some Tailwind classes and just a tiny bit of code at the top, so some glue code. You saw the login buttons there, etc. But everything is coming from the provider as well as the WAGMI providers. So basically no custom code. So we have a question. Would it be feasible to create an ETH address when doing the sign-in if a user doesn't have an ETH address and linking it, therefore allowing the user to just use an IC dApp without even caring if something will happen on the ETH side? So the question is, if you don't have an ETH address, why then most likely you wouldn't want to use the ETH login flow, right? Then I'd suggest you use the internet identity login flow instead, which allows you to do this, integrate with WebAuth, and so there, for instance, you can integrate with the fingerprint sensor on the computer and something like that. But yes, in theory, of course, you could generate an Ethereum address to be used for this login flow. But if you don't have a wallet and no address, then how is that information stored? It doesn't sound secure. But also, the backend canister is also represented by a unique address. And like I mentioned, your personal address is controlling the backend canister. That backend canister in turn can be represented by an Ethereum address that can use the EVM RPC interface or anything like to sign transactions on Ethereum, for instance. So we had a look at the main function here. There isn't a ton much more to say actually about the demo application. Let's have a look at how the application look. This is what's loaded when the login has completed. We have the message shown at the top was saying you haven't registered a profile yet, and we have the profile list. So just let's have a look at how the all profiles component look, because this shows you how sort of a real world application would interact with the internet computer using these techniques, and how straightforward it is. So now we have everything set up. We have an identity. And we have all these generated interface definitions, etc. So then we are actually using another support hook that is called use actor that uses another support library that I built that is called IC use actor. So what it does, it further simplifies the interaction with the backend canister. So it also provides a hook with a reference to a hook that exposes the backend canister to your whole application, and it also provides some utility stuff such as you can do sort of simple middleware functionalities where you intercept messages to back and forth if you want to have a look at them and maybe show some toast or whatever, or do some logging, etc. But when looking at this all profiles component, what we do here is that we use an actor that we use this hook that I set up earlier. And in the use effect of this component, I interact with the actor, and I call the list profiles function. And as you can see, this is fully typed and returned a list profile response, which is an array of user profiles that contains this basic information of avatar URL, name, and address. So once we have that, we can loop over that information and show these small profile cards. But all put together. So we are, to summarize what we're doing in the front end, we use an internet sign in with the Ethereum provider to make the identity context accessible throughout the application. We use an actor provider to make the backend, so the application backend available throughout the application. And then the rest is fairly straightforward. And now let's quickly have a look at how the backend works. This simple demo backend. So it defines 3 endpoints only. Get my profile, list profiles, and save my profile. And get my profile is, let's see here, save my profile. Once we have logged in, this is the first we interact with. We save my profile, we supply it with the name and this avatar URL, and then we want to save this information in the backend canister. And here's one interesting thing we're doing here, that we also need our backend canister to get access to the Ethereum address that we have used when logging in, right? But I haven't logged into the backend canister. I have logged into the sign in with Ethereum provider canister. But that's all good, because canisters can call each other. So in this really small utility function here, get address, what we're doing here is that we're using the pre-built interfaces that are provided for us when building the project to make a call from the app canister to the provider canister. And this also is fully typed. So the response here is a get address response, and if I have logged in, it will respond with a success or an okay response along with the address. Otherwise, it will return an error. So basically, if we haven't logged in before trying to save your user profile, it will generate an error and abort. Otherwise, if it doesn't abort, we have the address of the user. We can create the user profile object, and we can add it to the user profiles. The user profiles is a stable B-tree map that uses a feature of the Internet Computer, the stable memory feature, so that it will be there even if we upgrade the canister, etc. It will still be there. Basically, a key value store. So I guess that's sort of it for the demo front end and the back end. How much time do I get? Maybe I'll spend a few minutes talking about the sign in with Ethereum backend flow, showing you that repository as well, and then we can take some more questions. So let's have a look at the sign in with Ethereum provider. Now we have switched repositories. So now we're in the sign in with Ethereum repository. This service exposes a number of endpoints. The most important that are part of the login flow are these three: the sign in with Ethereum, the get delegation, the login, and the prepare login. First out, prepare login. That is the first thing that happens. After you have connected your MetaMask wallet, you need to prepare the login. And what it does is that it calls the sign in with Ethereum support library and asks it to prepare a login message for this specified address. So it is really straightforward interaction in the canister. And the prepare and how it looks in the support library is similarly fairly straightforward. This is how the message is generated. We have the settings that we provided during in the make file. We create this SIWE message, and then we convert that into a string format to send it back to the client. So now when we have completed the prepare login, the next step is the actual login step. And that is initiated after we have signed the message. The front end will call the login endpoint together with the signature of the message that we just signed, the message, the address of that did the signing, and a session key. And this session key is a random session key created for the purposes of this unique session. And that is generated in the front end. And here some more stuff happens that we added this information. Let's start here. First, we generate this Ethereum address that we can use inside the Rust canister based on the string version of that address that we had. So there we do some validation of the address. We also create a signature object based on the string signature. And there again, we do some validation to make sure that the signature has the right format, etc. So validating the address, validating the signature. And then we use the support library again, and now the login method, where we provide the signature, the address, the signature key, the signature map, which is a map where we store all currently in use sessions. So let's see here. Question. You mentioned multi-sig wallets. Can you explain a bit how SIWE could be used to do that? Would thresholds be for long principle to an ETH account? So this would be totally up to the implementing project, but a backend canister on in the internet computer can sign Ethereum transactions, and it can generate more addresses. So a canister can generate any number of addresses. And the signature, let me describe how that works. That uses the threshold signature scheme, which means that no node on the internet computer, no canister holds the whole private key needed to sign these transactions. So that is one of the key innovations in all of this, the threshold signatures. So basically, all the nodes in the network of a internet computer subnet has access to a small part of the private key needed to sign transactions. So when a canister wants to sign a transaction, it has to go through around a consensus, or it has to involve all the nodes on the network. And when you have reached a threshold of nodes, all sort of agreeing on signing that transaction, you can sort of form that signature without any of the nodes having access to the private key. And that is like one of the main differences compared to, you could of course build a Web 2 backend that signs Ethereum transactions, just put the Ethereum private key in your env file. And if you would like to use this technology to build a multisig, then you would have to define those rules. But that would be the scope of the project, to define these rules. So it's not something that is provided out of the box, but of course you can build that functionality internally in the canister, that you have a map of transactions that are initiated, and then you have a threshold. You define a threshold for each transaction, saying like, I want these 5 addresses. I want signatures from these 5 addresses before I, as a Canister, proceed to execute that transaction. Yeah, I'll get back to your responses there. Yeah, okay, that logic needs to be implemented in the Canister itself. Yes, tusen tack. So where were we? Once you have, what happens in the support library here during the login? Here's some stuff going on. Let's pick out the most significant pieces. When you do the login, you have the signature, the address, the session key, the signature map that holds all currently live sessions, and we have the Canister ID of the Canister. Let's see here. So what we do here is that we, based on, we convert the Ethereum address to bytes, and then we fetch the sign in with Ethereum message that we generated in the first step. So this is an important and cool and interesting thing. That basically here we are using the sign in with Ethereum message as its own nonce. Usually when you do an implementation using sign in with Ethereum, you include a small unique nonce in each message that you generate to make sure that it can only be used once, or that it, and in our case, we store an actual copy of the whole login message. And when the login call comes in, we fetch that generated message, and then we discard it. So basically, the message itself is used as a guarantee that you can only use one sign-in with Ethereum message once for login. So if you come across an old message, you wouldn't be able to use it later. So let's see here what's in the question. Okay, then the login is blah, blah, blah. Is it correct that the threshold signature inside Canister is pretty resource intensive and costs a bunch of cycles? Yes, it depends on what it costs. It doesn't cost much. It costs not a cent. It's just like $0.0001 or something like that. And there is also a limit to how many threshold signatures the internet computer can do at once. So yes, it's not the thing you might want to do if you need to do like thousands of transactions, that you want to build a Canister that does thousands of transactions per second or something like that. I don't have any cycle estimate for using sign-in with Ethereum and sign-in. There is a good web page on the Internet Computer documentation that clearly lays this out. To be honest, I've never memorized that, but it's cheap. And when you are building a real-world application, most likely you would want to create some kind of payment flow of some kind, and then it's easy to divert some of that flow to pay for the cycles that needed to create transactions. Okay, let's try to sum this up. Looking at the support libraries here and the provider Canister. Basically, we recover the Ethereum address based on the signature and the message. We compare them and see if the signer address is not the same as the address that we are expected, then that is a fail. And then, as I said, we remove this sign in the Ethereum message, disposing it to make sure that no one else can use it. And then we generate a seed that is what uniquely will identify this session or this user based on the it's based on the salt that we set in the settings, the user address, of course, and we can also include the domain of the website. And then we generate a public key based on all this information and return that to the user and or the front end. And in the last step, when the front end has access to this generated public key that it has received from the backend, it will then fetch this delegation object. It has to be done in 2 calls, because the first call is an update call where sort of this consensus is run and the information is added to this signature map. And then the second call, you get the delegation with a certificate proving that it's a valid signature, etc. And once you have that, the support hook can proceed to generate a delegate identity in the front end. And then you can start using that identity to make authenticated calls. And I think I'll stop there. There's, of course, a lot more to say depending on what level of detail we're going to. So let's see here, an odd question. By looking at all the repositories, how long did it take you to build this? An afternoon. Just to get a sense of effort going into this sign-in feature. So I was able to build this through thanks to a generous grant from the DFINITY Foundation. So I spent quite a bit of time to build all these support libraries, the hooks, and also the demos. But as you saw, if you would want to integrate this with an application, like say you want to build something similar to how this demo application that I built, then what I showed you is it's really straightforward. I'd say yes, it's definitely one afternoon integration into. If you have scaffolded the most basic internet computer application, it's like 2-3 hours tops to get started with the basic login flow. It's it's basically just adding the identity provider, creating this actor that simplifies the interaction with the backend Canister, and then you're good to go. And of course you need to configure this provider Canister, either if you have a build script or as I have a make file. But I would suggest, if you would like to get started, try this out during this hackathon or for some other project, to definitely fork my repository and use that as a starting point. Like I said, I try to keep the code base fairly clean and simple, so that it should be a good starting point for anyone starting to build. Yeah, and the Solana one, it works exactly the same as the Ethereum one. It's basically Solana based on the success of the sign-in with Ethereum standard. So this was not. I don't think it's fully a standard the same way as it is in the Ethereum ecosystem, but it's well supported in the biggest wallets, I think. So this all comes down to the wallet caring about this being a sign-in with Solana / Ethereum message for it to have this custom display. But it doesn't matter, even though the wallet doesn't support the sign-in with Solana standard. If it doesn't, that you can still sign the message, and that signature will still be valid. It will just not look as fancy or look as good as I showed you with it looked like a login message. Also, any plans on adding Svelte and or Solid.js support? I knew it. That question would come. Yes, this have been noted on a number of occasions. Actually, that there is no vanilla JS library for this, and there isn't. And of course, I should have built that from the get-go, but I didn't. And yes, it's on my to-do list to do that, and I would like to try out Solid.js. So maybe I'll try to do a Solid.js version of all this. But I do know that one project, OpenChat, have integrated support for this, and they are OpenChat. What's the URL? oc.app. They have integrated support for this, and they are, I think, using Vue, I believe. So here, sign in with Internet Identity, sign in with Ethereum, sign in with Solana. So maybe I'll nudge them and try to ask them, see if they have mentioned that they build a sort of a vanilla JS layer to make this possible. Can we have the link to what? To the OpenChat application? Yeah, it's, I don't know why it doesn't load. Yes, oc.app. Yeah, thanks. And that is basically one of the biggest IC applications. So I'm happy that they are using the libraries, and it's also some validation that the libraries and the provider Canister are safe to use in production. I think we are coming up to time. Do we have any final questions before we close this thing down?
As mentioned previously, I will have Kristofer's slides available, and we'll add them to the hacker pack. So you will be able to go through all of that information, as well as go through the recording of the session, which will be available in less than 24 hours. Usually should be like tomorrow morning, depending on where you live. But usually it takes us between 12 to 14 hours to get the recording up of the event. Can we get some cycles from the support team, please? Please do post about that in our Discord. We are in touch with the Internet Computer team, so we should be able to fetch some where needed. Other than that, thank you, Kristofer, for the exhaustive presentations. I think it was really nice seeing all these resources and all of this in action as well. Thank you all for the questions in chat as well. And yeah, see you all next week for the next workshops.
Cool. Thank you, everyone. It was really fun getting to present this.
It was great having you. See you all. Have a great day.